자, 여러분들 반갑습니다. 오늘은 그 8번째 강연이 되겠습니다. 지난 시간에 이어서 이 joint probability, joint distribution에 대해서 공부하도록 그렇게 하겠습니다. discrete case, if we x and y are two discrete random variables, we define the joint probability function x and y by probability x and y is equal to fxy, where if fxy are greater than equal to 0, summation and summation fxy is equal to 1. That's the sum of all variables x and y is 1. Suppose that x can assume any one of m values x1, 2, 3, m, and y can assume any one of n values yn 1, 2, n, then the probability of event that x equal xj and y equal yk is given by the formula 14. P probability of x and y is equal to fxy. The joint probability function for x and y can be represented by a joint probability table as shown in the table 2-3. The probability of x equal x1, 2, 3, m is obtained by adding all entry of the row corresponding to xi total f1 x1, f1 x2, f1 xm. The grand total of this joint probability is 1. For j equal 1 to m, these are indicated by entry totals in the extreme right hand column of margin of table 2-3. Similarly, the probability that y equal yk is obtained by adding all entries in the column corresponding to yk and is given by the formula 16. For k 1 to n, these are indicated by entry totals in the bottom row or margin of table 2-3, because the probabilities, the formula 15 and 16 are obtained from the margin of table. We often refer to f1 x and f2 y as the marginal probability functions of x and y respectively. It should also be noted that sigma fx equal to 1, sigma f2 y is equal to 1, which can be written formula as the formula 18, summation and summation fxy is equal to 1. This is simply the statement that the total probability of all entry is 1. The grand total of 1 is indicated in lower right hand corner of the table. The joint distribution function of x and y are defined by the formula 19. The table 2-3 fxy is the sum of all entries for which xj less than n equal to x and yk less than n equal to y. Continuous case. The case where both variables are continuous is obtained easily by analogy with the discrete case on replacing sums by integrals. Thus, the joint probability function for the random variable x and y is defined by fxy is greater than n equal 0. Integral fxy dx dy is equal to 1. Graphically, G is fxy represent a surface called the probability surface. As indicated in figure 2-4, the total volume bounded by this surface and the xy plane is equal to 1 in accordance with the property 2 above. The probability that x lies between A and B while y lies between C and D is given graphically by the shaded volume of figure 2-4 and mathematically by the formula 20. More generally, if A represents any event that will be a region Ra of xy plane that corresponds to it, in such case we can find the probability of A by performing the integration of Ra. That's P probability of A area region is equal to integral fxy dx and dy. The joint distribution function of x and y in this case is defined by function of x and y is equal to probability of x and y is equal to integral and integral f mu and nu d mu d nu. It follows in analogy with the formula 11 that the formula 23 that's the density function is obtained by differentiating the distribution function with respect to x and y. From the formula 22 we obtain probability of x is equal to f1x is equal to integral and integral f mu and nu d mu d nu. The probability of y is f2y is integral and integral f mu and nu d mu d nu. We call 24 and 25 formula the marginal distribution functions, or simply the distribution function of x and y respectively. The derivatives of 24 and 25 formula with respect to x and y are then called the marginal density functions, or simply the density functions of x and y are given by f1x is equal to integral fx nu d nu, f2y is equal to integral f nu y d nu. Let's talk about independent random variables. Suppose that x and y are discrete random variables if the events x and y is small y are independent event for all x and y, then we say that x and y are independent random variables. In such case, the probability of x and y is equal to probability of x multiplied by the probability of y. Or equivalently, fxy is equal to f1x multiplied by f2y. Conversely, for all x and y, the joint probability function fxy can be expressed as the product of a function of x alone and a function of y alone. X and y are independent. If, however, function of x and y cannot be so expressed, then x and y are dependent. If x and y are continuous random variables, we say that they are independent random variables if even large x less than and equal small x and large y is less than equal to y are independent even for all x and y. In such case, we can write probability of x and y is equal to probability of x multiplied by the probability of y. Also, we can say function x and y is equal to f1x multiplied by f2y, where f1x and f2y are the marginal distribution functions of x and y respectively. Conversely, x and y are independent random variables for all x and y. Their joint distribution fx and y can be expressed as a product of a function of x alone and a function of y alone. If, however, fxy cannot be so expressed, then x and y are dependent. For continuous independent random variables, it's also true that the joint density function fxy is the product of a function of x alone and the function of y alone, and these are marginal density functions of x and y respectively. Let's talk about change of variables. Given the probability distributions of one or more random variables, we are often interested in finding distributions of other random variables that depends on them in some specific manner. Product for obtaining these distributions are presented in the following theorems for the case of discrete and continuous variables. Discrete variables. Theorem 2-1. Let x be a discrete random variable whose probability function is fx. Suppose that a discrete random variable u is defined in terms of x by u equal pi x, where to each value of x there corresponds one and only one value of u, and conversely, so that x equal psi u, then the probability function for u is given by g nu equal f psi mu. Theorem 2-2. Let x and y be discrete random variables having joint probability function fxy. Suppose that two discrete random variables u and v are defined in terms of x and y by u equal theta x and y, v equal theta 2 x and y, where to each pair of values of x and y there correspond one and only one pair of value of u and v, and conversely, so that x equal psi u and v, y equal psi 2 u and v, then the joint probability function of u and v is given by g u mu u equal f psi mu nu psi 2 mu nu as the 32 formula. Theorem 2-3, let x be a continuous random variable with probability density fx. Let us define u theta x where x equal psi nu as in theorem 2-1. Then the probability density of u is given by g mu, where g mu vertical bar d mu vertical bar equal fx vertical bar dx vertical bar. Theorem 2-4, let x and y be continuous random variables having joint density function fxy. Let u define u equal theta 1 x and y, v equal theta 2 x and y, where x equal psi 1 u v, y equal psi 2 u v as in the theorem 2-2. Then the joint density function of u and v is given by g mu and nu, where in the formula 36, the Jacobian determinant, or briefly Jacobian, is given by the formula 37, like this. Okay, let's think about probability distribution of functions of random variables. Theorem 2-2 and 2-4 specifically involve joint probability function of two random variables. In practice, one often needs to find the probability distribution of some specified function of several random variables. Either following theorem is often useful for this purpose. Theorem 2-5, let x and y be continuous random variables and let u equal theta 1 x and y, v equal x. The second choice is arbitrary. Then the density function for u is the marginal density obtained from the joint density of u and v as founded in the theorem 2-4. A similar result holds for probability function of discrete variable. Theorem 2-6, let fx y be the joint density function of x and y. Then the density function of g mu of the random variables u equals theta 1 x and y is founded differentiating with respect to mu, the distribution function given by g mu equal the probability of theta 1 less than and equal to mu is integral and integral f x and y dx dy, where r is the reason for which theta 1 x and y are less than and equal to mu. Let's talk about convolutions. As a particular consequence of the above theorems, we can show that the density function of the sum of two continuous random variables x and y, that's of u equal x plus y having joint density functions f, x and y is given by g mu equal integral fx mu minus x dx. In the special case where x and y are independent, fx and y equal f1x multiplied by f2y, and the 39 formula reduced to gu mu equal integral f1x f2 u mu minus x dx, which is called the convolution of f1 and f2 abbreviated f1 star f2 star means multiplication. The following are some important properties of the convolution. First, f1 multiplied by f2 is f2 multiplied by f1. Commutative relationship. Second is associative relationship. Third is distributed laws of algebra with respect to operation of convolution. Okay, the next topic is conditional distributions. We already know that if probability of A is greater than 0, P probability of B given A is probability of A and B divided by probability of A. If x and y are discrete random variables, we have the event A, B, then become probability of y given by x is fx and y divided by f1x, where fxy equal pxy is the joint probability function and f1x is the marginal probability function for x. We define like the formula 43 and call it the conditional probability function of y given x. Similarly, the conditional probability function of x given y is f x given y equal fxy over f2y. We shall sometimes denote x given y and fy given x by x given y and f2y given x respectively. Conditional distribution. These ideas are easily expanded to the case where x and y continuous random variables. For example, the conditional density function of x or y given x is function of y given x is function x and y divided by f1 x, where fxy is joint density function of x and y, and f1x is the marginal density function of x. Using the formula 45, we can, for example, find the probability of being between C and D given that small x is less than large x, less than large x plus delta x is the formula 46. Generalization of these this result are also available. Application of geometric probability. Various problems in probability arise from geometric considerations or have geometric interpretations. For example, suppose that we have a target in the form of a plane region of area K and a portion of it with the area K1 as in figure 2DC 5. Then it's reasonable to suppose that the probability of hitting the region of area K1 is proportional to K1. We thus define like P, the probability of hitting region of area K1 is K1 over K, where it's assumed that the probability of hitting the target is 1. Other assumptions can of course be made. For example, there could be less probability of hitting outer areas. The type of assumption used to define the probability distribution function. 오케이. 오늘은 여기까지 하겠습니다. 26분간 제가 녹음을 했는데 여러분들 하여튼 집중해서 잘 이해하시기 바랍니다. 다음 강의에서는 이 노멀 디스트리뷰션 정규 분포에 대해서 계속해서 연강을 하도록 그렇게 하겠습니다. 여러분 수고하셨습니다.